You are there above the north pole of Jupiter, and the dark keeps flashing orange beneath you like fire under black glass. The subject is a thin layer high above Jupiter, older than our cameras and quieter than the storms below it. If that layer is doing things NASA cannot explain, then one of the most studied planets in the sky is still hiding rules we do not understand. And the story only gets stranger from here. Stay with me and join this channel for space stories that turn one weird clue into the bigger picture you can carry with you long after the screen goes dark. From far away, Jupiter looks familiar in the wrong way. A striped giant, a red storm, a world so famous it can feel finished. The kind of planet we think we already know. But up close, in infrared light, Jupiter stops looking like a smooth ball of gas and starts looking like a machine full of secret rooms. That is what the James Webb Space Telescope keeps finding. Not one neat answer, but a set of odd signals inside Jupiter's atmosphere and above its clouds. A fast jet where no one had seen one before. Dark arcs, bright spots, and a kind of glowing mismatch that made one scientist say, in plain words, that they were scratching their heads. To see why this matters, we need to step back. Most people believe Jupiter's real mysteries are deep down in its hidden core, or out at the poles where the auroras rage. The high atmosphere away from those obvious spectacles is supposed to be simpler. A place shaped by sunlight, known winds, and rules that big telescopes and old spacecraft have mostly worked out. Jupiter has always looked like the loudest planet in the room. It is so big that more than 1,300 Earths could fit inside it. Its storms can last longer than human lives. Its magnetic field is so strong that it grabs charged particles, bends them, and lights the poles with glowing curtains that make Earth's northern lights look small and shy. That is part of the problem. When a planet is famous for being extreme, we stop noticing the quiet places. We stare at the Great Red Spot. We watch the moons. We follow the giant auroras over the poles and assume the thinner layers in between are mostly background. For years, that seemed fair. Ground telescopes could see pieces of Jupiter's upper air, but not with enough sharpness to catch every small change. Earlier missions gave us layers of the puzzle, not the whole stack. The lower clouds showed belts, storms, and ammonia ice, while the highest hazes often looked soft and blurred, like breath on a cold window. Scientists built a sensible picture from that. Near the equator, far from the brightest auroras, the upper atmosphere should be fairly even. Jupiter gets only about 4% of the sunlight that Earth gets, so if sunlight is the main driver there, the glow should not break into wild little shapes for no reason. Even the parts above the Great Red Spot looked, at first glance, like they might be dull. That is not an insult. It is just how science works. You point your best tools where the signals should be simple, because simple places help you test old ideas and catch clean numbers. Back in 2017, teams planned early Webb studies of Jupiter with exactly that spirit. One proposal, led by Imke de Pater of the University of California, Berkeley, and Thierry Fouché of the Paris Observatory, was designed to show what Webb could do in the Jovian system. Jovian just means related to Jupiter. The plan was careful, smart, and built around places where the atmosphere seemed steady enough to teach them something basic. Then Webb launched. Then the mirror opened. Then this new eye began staring at Jupiter in infrared light, the kind of light our eyes cannot see, but warm gas and high hazes can. And suddenly the old map of what was supposed to be boring started to look thin. Infrared matters here because Jupiter is layered like an onion made of storms. Some wavelengths see deeper, some see higher. That means if you compare Webb with Hubble or with older spacecraft, you are not just taking prettier pictures. You are slicing the planet by height, like looking through floors in a building. In July 2022, Webb turned toward Jupiter and began collecting the kind of data scientists had waited years to get. Its near-infrared camera, called NIRCam, and its near-infrared spectrograph, called NIRSpec, could track details in layers roughly 20 to 50 kilometers above the cloud tops. That is high enough to leave the main weather decks below. It is also exactly where old assumptions started to crack. One Webb team, led by Ricardo Hueso of the University of the Basque Country, used those 2022 images to follow tiny features in a bright equatorial haze. Hueso later said the team was totally surprised. What had looked like a blurred band now showed crisp details they could track as Jupiter spun. That alone was a warning sign that the old picture was too simple. Another team looked above the Great Red Spot. Henrik Malin of the University of Leicester led that work. The region had been expected to be plain, lit mostly by sunlight, a quiet middle zone between deep weather and magnetic fireworks. Instead, the data would later be published in Nature Astronomy in 2024 as a message from a planet that was anything but quiet. If you had stood in a backyard and looked up at Jupiter before all this, none of that hidden drama would have been visible. You would have seen a bright point over the trees, maybe a steady cream-colored star with no twinkle. That simple little dot is part of why the assumption held so long. From home, Jupiter feels finished. From Webb, it feels alive. And by the end of those early observations, the familiar belief was standing strong but uneasy. The real secrets, many people still thought, must be deeper down or farther out. The thin upper air was not supposed to steal the story. But that picture is about to change. What we have just taken for granted turns out to be a small part of a much larger story. The surprise is not only that Jupiter is stranger than expected, it is that the strange behavior shows up in layers we thought were close to understood. Write the exact moment your picture of Jupiter shifted in the comments. That helps shape the next deep dive by showing which clue made the hidden planet suddenly feel real. Because once the old assumption cracks, the timeline of what Webb actually saw becomes hard to forget, and each step pulls the mystery closer to the center of the planet's living system. The story really starts with a place scientists thought would behave itself. Above the Great Red Spot, in the upper atmosphere, sunlight should have been doing most of the work. That was the expectation. A weak glow, a fairly smooth field, and maybe a few broad changes that could be explained without much trouble. What Webb found in July 2022 was not smooth at all. Using NearSpec, the team saw dark arcs and bright spots spread across the whole scene. Some of the features formed bands and curved shapes about 1,000 kilometers wide and as much as 6,000 kilometers long. Instead of a blank ceiling, the upper atmosphere looked like a pond hit by many hidden stones. That mattered because the glow they were measuring came from H3+, a simple ion made of 3 hydrogen atoms sharing charge. It is common in giant planets. It shines in infrared. Scientists often use it as a signpost for what the upper atmosphere is doing, how hot it is, and how energy moves through it. The expectation had been that H3+ around the Great Red Spot would be guided by fairly steady conditions. What they found was a field where the radiance, the amount of glow, changed by as much as a factor of 4. That is not a tiny wobble. That is the difference between a room lamp and a room lamp suddenly turned almost all the way down, then up again across a short distance. Inside the Great Red Spot itself, the H3+ signal was relatively dark. To the northwest and southeast, it brightened. That pattern alone said the old clean model was missing something. It was as if the storm below was tugging on the air above without touching it directly, like bass from a speaker shaking a glass on a shelf. Mullen's team suggested gravity waves. These are not the space ripples from black holes. These are atmospheric waves, more like the up and down motions air can carry after deep turbulence pushes upward. On Earth, gravity waves can form when air rolls over mountains or when storms punch into higher layers. On Jupiter, the Great Red Spot and the violent lower atmosphere may be launching those waves far above the clouds. That was the surprise pattern in full. Scientists expected sunlight to shape a rather even upper layer. Webb found structured bands and arcs. And the feeling of that switch is simple. What looked like smooth paint on a wall turned out to be wallpaper full of hidden seams. Soon after that, another clue arrived from the equator. The hazy, bright band near Jupiter's middle had long looked soft. Webb's NearCam turned that haze into something trackable. By watching tiny features shift over one Jupiter day, with images about 10 hours apart, the team could measure motion in a layer no one had mapped this way before. What they expected was a high haze with fine texture, yes, but not a major new wind system. What they found was a jet stream more than 4,800 kilometers wide. It was racing at about 515 kilometers per hour, or 320 miles per hour, around 40 kilometers above the cloud tops in Jupiter's lower stratosphere. That is faster than a strong Earth hurricane, and sitting in a place where the view had once blurred into guesswork. Ricardo Hueso said those old hazes suddenly appeared as crisp features. Michael Wong at UC Berkeley helped compare Webb's high-layer winds with Hubble views of deeper layers. That let scientists measure wind shear, which is the change in wind speed with height. In plain terms, it showed that the floors of Jupiter's atmospheric building were not moving together the way many people had pictured. Lee Fletcher of the University of Leicester added another piece. Jupiter has a repeating pattern of winds and temperatures high above the clouds. If the new jet is tied to that long rhythm, then its speed and altitude may change over years. So even the jet may not be a fixed road. It may be a moving road inside a moving sky. Already the old assumption was weakening. The upper atmosphere above obvious weather was not passive, it was being sculpted. Deep turbulence below could punch upward. Hidden rhythms could speed up winds far above the clouds. And the neat border between lower weather and higher air was starting to look like chalk in the rain. Then came the Christmas data. On December 25, 2023, Jonathan Nichols and a team at the University of Leicester used Webb's NIRCam to watch Jupiter's aurora in infrared light at 3.36 microns. At the same time, NASA's Hubble Space Telescope watched in ultraviolet. This mattered because the two observatories were looking at related parts of the same event through different windows. The expectation was reasonable. Auroras are bright because charged particles slam into the atmosphere near the poles and make gases glow. If Webb saw a bright infrared patch from H3+, Hubble should usually see some matching bright behavior in ultraviolet. The details might differ, but the big bright spots should still rhyme, like two cameras filming the same fireworks from different streets. That is not what happened. Nichols said the auroral region was fizzing and popping with light, sometimes changing by the second. The H3+ glow was far more variable than scientists had believed, and most striking of all, the brightest light in Webb's images had no real counterpart in Hubble's pictures. That mismatch is where the headline comes from. NASA did not say the planet broke physics, but Nichols said very clearly that the team was scratching their heads. To explain the brightness seen by both telescopes, they would need high amounts of very low-energy particles hitting the atmosphere, a combination previously thought impossible. Then he said the line that matters most. We still do not understand how this happens. Think about that for a second. Not on a new exoplanet 700 light-years away. Not in a galaxy from the early universe. On Jupiter, the bright giant school kids can spot from a driveway, one of the most watched worlds in the solar system. Scientists found a glow pattern their current picture could not cleanly explain. The surprise pattern showed up again. They expected auroras to change more slowly. Webb saw second-by-second flickering. They expected the two telescopes to show matching bright structures. Instead, the strongest infrared light stood apart, like hearing a drumbeat through the wall with no dancer on the floor above. That oddity points to a deeper truth. Jupiter's aurora is not just a light show painted by the sun. The planet's own magnetic field grabs particles from many places. It captures material from the solar wind. It also grabs particles thrown out by Io, the volcanic moon that sprays matter into space like a dirty snow machine circling a giant magnet. Those particles do not all arrive with the same energy. Some are fast, some are slower. Some may rain down in ways older models grouped too simply. Webb's H3+ data says the heating and cooling of Jupiter's upper atmosphere is changing fast. Hubble's mismatch says the particle recipe driving that glow may be stranger than the textbook version. And now the earlier clues start talking to each other. The bands and arcs above the Great Red Spot suggested that deep weather could shape the upper atmosphere. The fast equatorial jet showed that hidden structure can live high above the clouds. The aurora mismatch said energy from space is not entering that upper atmosphere in the way scientists expected. Below, weather is pushing up. Above, particles are raining down. In the middle, the air is not quietly waiting for instructions. This is why the word inside matters, even if Webb is not seeing Jupiter's buried core. It is finding surprises inside Jupiter's system of layers. Inside the exchange between clouds, waves, charged gas, and magnetic forces. Like opening a machine and learning that the belts, fans, and wiring are all shaking each other at once. By about 2/3 of the way through this story, honesty matters more than neatness. Scientists do not fully agree on every cause here. The 2024 Nature Astronomy paper argued that wave dynamics may dominate the short-term behavior above the Great Red Spot. But the same study also said there is no full modeling consensus on how much gravity waves heat Jupiter's upper atmosphere, or exactly how heat gets redistributed from pole to equator. That hesitation is not weakness, it is the sound of real science. A tidy story would say one cause explains all the clues. The real story says several systems may be overlapping. Gravity waves may be shaping some regions, particle rain may be driving others. Long atmospheric cycles may change what Webb sees from year to year. In parallel, other spacecraft add texture without closing the case. NASA's Juno mission has spent years diving over Jupiter's poles and sampling its magnetic environment. Those measurements help frame the aurora, but even with Juno in the picture, the new Webb and Hubble mismatch stays hard to pin down. The puzzle did not vanish when more data arrived. It got sharper. And that sharpness changes the scale of the mystery. A lot of people imagine giant planets as simple in the wrong way. Too big to touch, too gas-rich to visit. Interesting, yes, but mostly settled. Webb's results suggest the opposite. Jupiter may be one of the best places in the solar system to watch a planet fail to stay in separate boxes. Weather is not only weather there. Magnetism is not only magnetism. Light is not only a pretty glow. Each clue keeps spilling into the next one. A storm may send waves upward. A high jet may reveal a rhythm no one had mapped. A bright aurora may refuse to line up across wavelengths. And each time scientists expect a clean answer, Jupiter hands them a moving target. By the time the 2025 Nature Communications paper arrived, the real reveal was no longer one strange image. It was a new way of seeing the whole planet. Jupiter's upper atmosphere is not a quiet roof over the storms. It is an active exchange layer. It is where the lower atmosphere, the ionosphere, and the magnetosphere keep passing energy back and forth. So the thing NASA does not yet know how to explain is not a single glowing dot. It is a behavior, a mismatch, a pattern of energy moving through Jupiter in ways that do not fit the old picture. And once you see that, the giant planet stops being a finished object in the night sky. It becomes an unfinished conversation. And here is where this stops being about one planet and begins being about us. If the reveal in this story is right, then the way we think about giant worlds quietly shifts for anyone who studies weather, magnetic fields, or life-friendly environments around other stars. Jupiter becomes more than a local giant. It becomes a training ground for how planets behave when deep atmosphere and space weather refuse to stay apart. Share this with one friend who thinks the solar system has already given up its big secrets. That one send is useful because these stories land best when someone realizes, in real time, that a familiar world is still changing under our eyes. What happens next matters beyond Jupiter, because every better model of this planet becomes a better model for other giant planets we cannot visit so easily. The changes begin in the way scientists ask their next questions. Instead of treating Jupiter's upper air as a thin layer to sample and move past, they have to treat it as a crossroads. A crossroads means traffic from more than one direction. Energy rises from below, particles arrive from above, and the response can flicker by the second or stretch across years. That affects the next Webb observations. If astronomers return to Jupiter's aurora at 3.36 microns and catch the same kind of mismatch with Hubble again, the case gets stronger. If the mismatch changes with time, that matters too. A repeating mystery tells you there is a missing rule. A changing mystery tells you the rules themselves may depend on conditions we have not measured well enough yet. It also changes how people read the older clues. The jet found in July 2022 may not be just one odd ribbon of wind. If Lee Fletcher is right about a link to larger stratospheric cycles, then the jet could be part of a timed pattern that rises and falls over roughly 2 to 4 years. That means a planet that once looked stable in snapshots may only make sense as a movie. The structures above the Great Red Spot become more important as well. The 2024 Nature Astronomy result suggested that wave-driven disturbances can shape the ionosphere, the charged part of the upper atmosphere. That sounds technical. In simple terms, it means a storm far below may shake the upper air the way a subway train can rattle dishes many floors above the tracks. And that is a domestic anchor worth keeping. When your phone shows a weather map, you are looking at layers of motion over one place. Wind at ground level can differ from wind above the clouds. Now imagine that, but on a world with no solid surface, with a magnetic cage around it, with volcano-fed particles arriving from a moon, and with storms older than some nations. Jupiter is not just weather, it is weather wired into space. Future missions will test that picture in sharper ways. ESA's Jupiter Icy Moons Explorer, called JWST, launched on April 14, 2023, and is scheduled to reach the Jupiter system in July 2031. Its main targets are the moons, especially Ganymede, Callisto, and Europa. But to study those moons well, it also has to study the giant planet's environment, including the charged particle soup the moons live inside. NASA's Europa Clipper, launched on October 14, 2024, is on a path to the Jupiter System 2, with arrival planned for 2030. Its job is Europa. Still, No mission can examine that moon in isolation. Europa flies through Jupiter's magnetic world, so every better idea about how Jupiter moves energy around helps scientists ask better questions about the moons as well. This reaches farther than our own system. When astronomers study giant exoplanets around other stars, they often have only thin slices of data, a glow here, a spectrum there, a shift in brightness over time. If Jupiter, the world we can study best, hides unexpected coupling between storms, waves, and particle rain, then distant giant planets may be hiding even more. Webb is not just rewriting Jupiter. It is teaching caution everywhere else. That caution is healthy. The line from Jonathan Nichols in May 2025 matters because it is so direct. We still do not understand how this happens. There is power in that sentence. It tells younger scientists where the open doors are. It tells model builders where old assumptions may be too rigid. And it reminds the rest of us that discovery is not the end of mystery. Discovery often widens it. As the dates get tighter, the story gets sharper. July 2022 gave Webb the upper atmosphere structures and the fast equatorial jet. December 25, 2023 gave Webb the auroral flicker and the strange split from Hubble. June 25, 2024 brought the public release about the Great Red Spot structures. May 12, 2025 brought NASA's release on the Aurora mystery and the Nature Communications paper behind it. From here, the next steps are concrete. Repeat the Webb observations at the same wavelengths. Match them again with Hubble in ultraviolet. Compare both with Juno's record of particle conditions. Track whether the 515 km/h jet shifts in altitude near the roughly 40 km level above the clouds. Watch whether the H3+ brightness patterns return in the same shapes or reform in new ones. These are not tiny details for specialists only. They decide whether Jupiter's upper atmosphere is mainly being shaken from below, lit from above, or rebuilt by both at once. They decide whether the impossible-looking particle mix is truly impossible or just missing from older models. And they decide how we read every future flash of light over that giant striped planet. There is also something quietly human here. We like the idea that the nearby universe is a finished neighborhood. The moon is mapped, Mars is watched, Jupiter is famous. But fame is not understanding. The truth is closer to home and stranger than that. A world can sit in plain sight for centuries and still keep a hidden room locked. So what should you watch for next? Watch for repeat language from scientists. If future papers keep returning to words like variable, mismatch, coupled, and unexplained, that is a sign the new picture is holding. Watch for exact dates tied to repeated observations. Watch for whether Hubble and Webb are used together again. When two telescopes disagree in a useful way, the disagreement itself becomes a measuring tool. And keep one image in mind the next time Jupiter rises. Not just the bands, not just the Great Red Spot. Picture a high, dim layer above the clouds, changing shape while charged particles fall into it and hidden waves rise toward it. That is the real stage now. The action is not only in the famous storm, it is in the traffic between layers. What comes next will not look dramatic at first. It may arrive as another set of orange arcs, another curve in a graph, another sentence in a paper with a date attached to it. But somewhere in those numbers, someone is going to catch the next clue. Maybe it will show that the strange auroral mismatch repeats under a certain magnetic condition. Maybe it will show that the Great Red Spot sends more energy upward than expected. Maybe it will reveal that the jet and the glow are tied by a larger rhythm nobody has fully mapped. When that happens, Jupiter will widen again. Not in size, in meaning. A giant planet once treated as a familiar backdrop will become a live test bench for how worlds breathe, glow, and trade energy with space. And every new observation will matter twice, once for Jupiter itself and once for the distant planets we can only study by their light. I keep coming back to one date, December 25th, 2023. A telescope sitting far from Earth watches Jupiter's pole at 3.36 microns, and the glow there starts popping second by second. Hubble watches too, and the brightest infrared feature refuses to show a proper ultraviolet twin. That is such a small thing to describe. It is also the kind of small thing that can force a whole field to rethink a planet. Save this video and come back the next clear time Jupiter is up where you live. That quiet habit gives you a personal marker for how fast our picture of the giant planet is changing. Because the future of this story is not a closed answer. It is another observation, another mismatch, another brave sentence from a scientist saying we do not know yet. And on a world as restless as Jupiter, that is exactly why the next discovery is already on its way.